Let's talk about how do we use the Doppler effect equation. So we'll be discussing the 4 scenarios that we discussed in the part 1 video. Then from there, we try to make a summary of what happens in these 4 scenarios. So the 2 of the scenario is you have the observer moving away from the sound source, or you have the sound source moving away from the observer. So observer and sound source. If the observer is moving away from the sound source, this is the first scenario. If the sound source is moving away from the observer, then it will be the second scenario. So both of these scenarios here share the same characteristics, in which if the observer is moving away from the sound source, the distance between the observer and the sound source increases. Whereas if the sound source is moving away from the observer, the distance between the sound source and the observer increases as well. So both of them share a similar characteristics, in which the distance between the sound source and the observer increases. Okay, so if you are looking at the Doppler effect situation, in which you see the sound source and the observer are getting further and further apart, you know that the apparent frequency observed by the listener will be less than the actual frequency of the sound wave produced by the sound source. It is not because the distance increases, therefore the apparent frequency is less than the frequency of the sound source, frequency of the sound waves produced by the sound source. Okay, it's not because of a distance that this happened. It is because of this moving away and moving away, therefore this happened. But both of them share the same characteristics. Therefore, an easier way for us to distinguish is if we see the distance is getting further and further away, we know the frequency perceived by the listener will be less than the frequency of the sound wave produced by the sound source. Okay, again, it is not because the distance increases. It is because it's moving away, or it is because of these two scenarios over here. Why these two scenarios causes the apparent frequency to be less than the frequency of the sound wave produced by the sound source? This one you have to refer to the video in part 1. Okay, then you have a third and fourth scenario. One is the observer moving towards the sound source, so something like this. Or you have the sound source moving towards the observer. So both of them share a similar characteristics, in which the distance between them will decrease. And if you see the distance between the sound source and the observer decreases, you know that the apparent frequency will be greater than the frequency of the sound wave produced from the sound source. So if the sound source is producing a wave of 300 hertz, what you might hear is a wave, well, it's a sound with a frequency of 320 hertz, let's say. So the frequency listened by the observer will be higher than the frequency produced by the sound source. Okay, so is it because of the distance decreases that this happened? Not really. It is because of one object is moving relative to another object, therefore you get a change in the frequency perceived by the observer. It's not the distance that matters. It's the fact that one is moving relative to another one that matters. Okay, so next, this is the equation for Doppler effect. So we are going to use this equation to determine the apparent frequency. So let's look at what are the variables in this equation over here. This F here represents the frequency of the sound produced by the sound source. So this is the frequency of the sound coming out from your guitar or coming out from your speaker, whatever it is, the one that produced the sound. Whereas on the left hand side of the equation, you have F subscript A. A represents apparent. Apparent means by it's the one that is perceived, observed. Okay, so this apparent frequency here is the frequency of sound listened by the observer, or it can be detected by a phone mic or microphone, let's say detected by a microphone, any kind of receiving machine. Okay, so your ear is also a receiving end, so it's a frequency of sound listened by the ear of the observer. Okay, so this one is the source, this one is the observer. Okay, then next you have this V over here. This V here represents the wave propagation speed of the sound wave in the medium. Okay, if your medium is air, then it's usually 343 or 340 or 330, depending on the humidity and the temperature of the air. But this value here is usually given in the question. But if it's water, then it's definitely not 343. If it's traveling in like a liquid, like a paraffin oil, then of course it's another wave propagation speed. The wave propagation speed of the sound wave depends on the medium. So if the medium is atmospheric air, then it's 343 meter per second. If it's helium, then it's another value. Okay, so in usual cases, Doppler effect usually happens in atmospheric air. Therefore, most of the time is 343 meter per second. But it's not all the case, most of the case. Okay, then next you have this V subscript O and V subscript S here. V subscript O here represents the speed of the observer. It can be moving away, it can be moving towards. You don't need to care about the direction. You just need to know the magnitude of it. The V subscript S here is the speed of the sound source. So the sound source again can be moving toward or moving away. You don't need to worry about whether it's positive or negative. This one is just the magnitude. The sign here is the one that we need to be more careful about. This sign here depends on the direction of the motion of the observer or the direction of motion of the sound source. If it's towards, then it can be a certain sign. If it's away, it can be a certain sign. Most of the time, many students can't really memorize which situation use plus, which situation use minus. And to be honest, I myself also have the problem to remember what is which situation to use plus, which situation to use minus. So here is my way of doing it, and if I'm doing it this way, I don't need to remember which one is plus, which one is minus. What I do is I reverse engineer the equation based on my understanding over here. Okay, so what's the step of me using this equation here? First, I determine whether the sound source or the observer is stationary. Because if I know one of them will be stationary in our syllabus. So if the observer is stationary, then V subscript O will be 0. If the sound source is stationary, then V subscript S will be 0. So if the observer is stationary, then V observer will be equal to 0. Then what happens is this part of the equation will disappear. Then what's inside a bracket will be V divided by V plus minus Vs. So V here is the wave propagation speed of the sound wave in the medium, whereas this V subscript S here is the motion, the speed of the motion of the sound source. So the sound source moving to the left or moving to the right, what's the speed? Okay, so this plus minus here, we will determine the sign in the later steps. Okay, if our sound source is stationary, then V subscript S will be equal to 0. Then what happens is this part of the equation will disappear. Then what is inside our bracket will be the speed of sound in the medium plus minus the speed of the observer moving divided by the speed of the sound in the medium. Okay, so this will be what appear inside our bracket. So from this equation, you will modify what is inside this bracket in the next line. After you've determined step 1, you move on to the next line, you simplify the bracket. Next step, you determine whether the distance between the sound source and the observer is increasing or decreasing. If you know the distance is increasing, it's getting further and further away, either the observer move away or the sound source move away. If that happens, then the distance between them increasing, and you know that the apparent frequency will be less than the frequency produced by the sound source. So you know the apparent frequency is less than the frequency of the sound wave produced by the sound source. Whereas if the distance between the sound source and the observer decreases, it can be a sound source moving towards observer or observer moving towards sound source. When that happens, then you know that the apparent frequency will be greater than the frequency of the sound wave produced by the sound source. Then you know the apparent frequency is greater than the frequency of the sound wave produced by the sound source. Observer will have a greater frequency compared to the frequency of the sound source. Okay, so now you have known that already. What you need to do in the next step is to reverse engineer it. Reverse engineer to determine what sign you need to put in here, whether it's a positive sign or a negative sign. So let's say, let me give you an example. Let's say that observer is moving towards a sound source, something like this. Observer moving towards sound source. Sound source is stationary. Sound source is stationary, we will be using this bracket. You have made sound source speed to become 0. So this is our bracket. Then we know that the observer is moving towards the sound source. Therefore, the distance between the sound source and the observer is decreasing. So if decreasing, then we know that our apparent frequency will be greater than the frequency of the sound wave produced by the sound source. So we know that our answer will be larger than this side. Okay, so this will be larger, this will be smaller. So what is inside this bracket here must be greater than 1. Okay, if f apparent is equals to 1 times f, then f apparent will be equals to f, right? If f apparent equals to 1.2 times f, then f apparent will be greater than f. So we want a value inside the bracket which is larger than 1. Okay, so if you want to make the value inside this bracket to be larger than 1, should you put a plus here or should you put a minus here? Well, we should put a plus, right? Only what appears up here will be greater than what appears down here. The numerator will be greater than the denominator. Therefore, our f apparent will be greater. Therefore, you change this to a positive sign. Okay, you determine whether the answer is larger or smaller than the f first. Then after you determine it, only you see in order to make it larger or in order to make it smaller, should I use a negative sign or should I use a positive sign? We'll reverse engineer back the sign. This is what I usually do. Let me give you another example. Let's say the sound source is moving away from the observer. Sound source moving away from the observer. So the observer is not moving, so we are using this bracket over here. We make the speed of the observer equals to 0, then this is our bracket over here. So we need to determine this sign later. Step 2, we say that the sound source is moving away, so the distance between the observer and the sound source will increase. So if we know it increased, then we know the apparent frequency will be smaller than the frequency of the sound wave produced by the sound source. We know that this value here will be smaller, this value here will be larger. Therefore, we want what happens inside this bracket here to be smaller than 1. Because let's say f apparent equals to 0.8 times f, then of course f apparent will be smaller than f, right? So we want what happened inside the bracket here to be smaller than 1. So the bracket that we are using is this one. We are using this bracket here. The observer is stationary. We are using this bracket and we want to make this one here smaller. So if we want to make the f apparent smaller, should we plus or should we minus over here to make this value to be smaller than 1? We should put the plus, right? If we put the plus, then the value down here will be greater than the value up here. Numerator smaller than denominator, it will be like 8 over 10. So you get a number which is smaller than 1. So you know you need to put a plus here, so you change it to a plus, then you put in your substitution, then you get your apparent frequency. Again, reverse engineer it. First, determine which kind of bracket we will end up with, then determine whether your answer will be bigger or smaller. If your answer is bigger than f, then you need to make the bracket larger than 1. If the f apparent is smaller than f, then you need to make the bracket smaller than 1. So how do you make it? You determine whether you need to put a plus or put a minus to make it bigger or smaller than 1. That is how I usually use the Doppler effect equation. Okay, I can't really remember what direction it will be plus, what direction it will be minus. Usually I just do it this way. I reverse engineer it. Okay, so this is how I use the Doppler effect equation. Now let's apply this equation in the same situation we discussed in the previous video. So we have a jet moving towards a soldier. So in this case, it will be moving towards here, then the frequency, apparent frequency will be higher. Then once the jet moves past this soldier over here, then it is the sound source is moving away from the observer. Therefore, you should expect a lower frequency, a lower pitch. So it'll be something like this. Okay, so if we plug it into the equation, the first portion of the journey, I'll be able to pause the video. Okay, the first portion of the journey, you use this equation over here. Because the sound source is moving, the observer is stationary. So if the observer is stationary, then the V observer will be equals to 0. Then you are left with what is here inside the bracket. Then you have to decide whether this is positive or negative. So you need to decide first whether the frequency should be higher or lower. So you know that the distance between the sound source and the observer is getting smaller and smaller. The jet plane is moving towards the observer, so the distance between the sound source and the observer gets smaller and smaller. If the distance decreases, then you know it should come out with a higher apparent frequency. higher apparent frequency if the distance is decreasing. So higher frequency means by you need this bracket here to be greater than 1. So how do you make this bracket here greater than 1 when you only have one sign to change? You have to make the down here, you have to make the denominator smaller than the numerator. So how do you make the denominator smaller? You put a negative sign. Okay, that's why you change this plus minus to a negative sign, then you get your answer for apparent frequency. Next, for the second portion of the journey, again the observer is not moving, so V subscript O is equals to 0. Now we are left with plus minus the speed of the sound source. So we have to determine whether it's a plus or a minus over here. We have to see whether the distance between the sound source and the observer is increasing or decreasing. So this is a soldier, this is the jet plane flying over it. So the distance between the sound source and the observer is increasing. If the distance is increasing, then we expect the apparent frequency to be lower than the frequency of the sound wave produced by the sound source. So if this F apparent is smaller, then therefore we need to expect what is inside the bracket here to be smaller than 1. When you are able to get a value for apparent frequency which is less than the frequency of the sound wave produced by the sound source. So this bracket here needs to be less than 1. So how do we change the denominator in order for the bracket over here to be less than 1? We have to make the denominator larger, right? If you make a denominator larger, then this value here becomes smaller. So it will be less than 1. So how do you make the denominator larger? You put a plus here. Then you make the denominator larger. Then this value here will be less than 1. So something less than 1 times F will get you something which is less than the F over here. So this is how you apply the equation in this case over here. Okay, please take note that this jet here is flying with a constant speed. It is not speeding up, it is not slowing down. So we know that the speed of the sound wave here is around 340. This one never changed, it's constant. The speed of the sound source, let's say, is 100 km per hour. This one is also fixed, not changing. Fixed, fixed, fixed. The frequency of the sound produced by the sound source is also fixed. That's why this everything here, every parameter inside the right hand side of the equation here is constant. That's why the frequency apparent, the one that is observed by the soldier here, is constant throughout the journey here. The frequency never changed throughout the journey from here to here, because everything here is constant value. But this frequency that the soldier listens is greater than the frequency of the sound produced by the jet. That one is greater. It's a higher frequency. It's a higher pitch compared to the pitch produced by the jet over here. But that pitch here remains constant throughout the journey. Unless the speed of the sound source increases, then this value here get larger and larger. Then this bracket here get larger and larger. Then this apparent frequency gets larger and larger. That's when the speed of the jet increases. When the speed of the jet decreases, then this value gets smaller and smaller. Then this value here will get closer and closer to 1. Then you get nearer and nearer to the actual frequency produced by the sound source. So the frequency will go from a high frequency to a frequency produced by the sound source. Okay, that is if your jet slows down to a stop. Okay, if you look at this side of the equation, again the speed of the sound in air, if it's in air, then it's fixed 343 or 340. The speed of the jet plane is constant, so this one is constant, constant, constant. Then the frequency here is decided by the speaker in the jet. That one is constant as well. So everything here is constant, therefore the apparent frequency should be constant as well. That's why throughout the journey of the jet moving to the right, the frequency is constant. Okay, just that this frequency here will be lower compared to the frequency produced by the speaker at the jet. The speaker at the jet might produce a frequency of but what the soldier might listen is a lower pitch but a constant frequency, constant pitch. Okay, so the pitch will remain constant, just that it experiences a drop when it passed by the soldier. That's the idea of Doppler effect.